Hello, today we are discussing basic electronics, PN junction diodes and its applications. This is module 2. The topics to be discussed today are the negative clamper with positive bias, negative clamper with negative bias, voltage multiplier and its types, half wave voltage doubler, full wave voltage doubler, voltage tripler and voltage quadrupler. Now this is a typical clamper circuit with positive bias. Why it is positive bias? Because the positive terminal voltage is facing the diode. So that is why it is a positive bias. But thing is that as the diode negative terminal is facing positive voltage, therefore it is of reverse bias. So whenever the signal is applied at the input side, initially it at 0 volt, therefore diode positive side is at 0 volt and the negative side is at plus V volt. Therefore the diode is reverse biased until and unless the input signal crosses the voltage level VB. So when it is crossing the voltage level VB, the diode becomes forward biased and therefore we are getting the sweep. That means we are getting the voltage across the resistor. So this is the way by which the clamper circuit works. So therefore if we look at into the graphical waveform, it shows that the signal has been reduced to, the average value of the signal has been reduced to minus VB. That means from minus VB it is gradually clamping, it is gradually moving up and thereafter it is reaching the peak value and then it is falling again below to the its negative. So if we look into the output voltage, that is V0, so across the diode it is V0 minus VB. So if V0 minus VB is equal to minus Vm, therefore the V0 will be equal to VB minus Vm. So therefore the average value is minus Vm plus VB. That is why it is in the negative domain, the average value, but it is in such a position that the positive sweep is not totally in the fourth quadrant, but a little bit it is coming out in the first quadrant. So this is the nature of the clamper circuit with positive bias, where we are seeing a fractional positive sweep is coming out of the coming into the first quadrant. And this is the negative clamper with negative bias. Now here what happens when the diode is starting when the input signal is starting to flow at that time, as the negative voltage is applied to the negative terminal of the diode, therefore the diode will be forward biased, and therefore what will happen if we look into the capacitor will be charged on the right side negative and the left side positive. So it is the minus Vm minus Vb is the amount of voltage which is appearing for the output voltage. So therefore capacitor is charged up to minus Vb minus Vm with negative polarity on the right hand side. So therefore whenever we are applying input signal, the average value will be reduced to minus Vb minus Vm. So therefore it is clamping down circuit, and we are seeing the positive peak value has been it is well below the horizontal axis. So that is why the waveform has been sufficiently clamped down. Now if we increase the potential magnitude of VB in the negative voltage, then what will happen? The signal will be gradually moving down more and more. And this is the voltage multiplier. In the voltage multiplier we are seeing that it is a half wave voltage doubler, full wave voltage doubler, voltage tripler, voltage quadrupler. These are the varieties of examples of voltage multiplier, and it is obvious that is voltage multiplier is possible because we already have seen that if we increase the time constant of the circuit, then the amount of charge which is possible to be stored in the capacitor will be charged instantly, but it will take long time to discharge. So that is why the discharging path delay will not allow the capacitor to discharge. So this is the half-wave voltage doubler in which the connection of the diode is shown and the capacitor correspondingly. So signal is first in the first cycle, signal is flowing through the capacitor and then the diode D1 is forward biased. In the negative cycle, the diode D1 is reverse biased, but through capacitor C2 and diode D2 the signal is flowing. So therefore what happens, so initially the capacitor C1 is charged negative on the right hand side because the diode D1 is forward biased under the positive sweep only. So therefore on the right side minus and left side plus, in this way the capacitor 1 will be charged up to minus Vm, and thereafter when the diode D2 is working at that time, capacitor C2 is bottom side positive and top side negative. In this way it will be charged up to minus Vm. But what will happen, it is already flowing through capacitor C1, that is which is on the left hand right hand side negative minus Vm. So therefore the output voltage V0 will be equal to 2 times of Vm. And here the full wave voltage doubler example is given, in which there are two number of diodes. One diode is facing on the right hand side and other diode is facing on the left hand side. So it is a connection in which the for positive sweep diode D1 is forward biased and for the negative sweep diode D2 is forward biased. So therefore when the diode D1 is forward biased, the capacitor C1 is charged, and when the diode D2 is forward biased, at that time capacitor C2 is charged. So therefore the two number of capacitor contributes Vm each. So overall output voltage we will get, it is 2 times of Vm. So therefore the output waveform we are getting little bit ripples are present, but still it is 2 times of the peak of the message magnitude, which is almost constant over the total period, or for a long time we are getting, it is almost equal to 2 times of Vm. So therefore it is a voltage doubler circuit. And this is a typical voltage tripler circuit in which the diode D1 is forward biased under the positive sweep only. Therefore the capacitor is charged up to the peak value of the message signal only in the forward half, a positive half, in which left side is positive and right side is negative. And for the negative sweep of the input signal at that time, the capacitor C2 is charged due to D2 is forward biased. And when the D2 is forward biased, we can see that bottom side positive and top side negative. In this way, and the voltage across the capacitor C1, the total voltage due to C1 and the signal generator, we are getting 2 times of Vm, is the amount of peak value by which capacitor C2 will be charged. So therefore the voltage which could be stored into the capacitor C2 is 2 times of Vm. Another is diode D3. D3 will be charged, D3 will be flown for the positive signal will be flown through D3 for the positive sweep of the input signal. So at that time what happens, the capacitor C3 is charged, but what is the voltage through which C3 will be charged? Because the path of the current is flowing through C1, C3, diode D3 and the message signal Vi. So here the voltage already stored in C1 is minus Vm, and voltage stored in C2 is 2 times of Vm. So therefore when C3 is charged, it might be charging up to 3 times of Vm, but what happens, due to the voltage present in the signal, which is also magnitude Vm but opposite in polarity, therefore 3 Vm minus Vm, 2 times of Vm will be charged up to 2 Vm will be charged to the capacitor C3. So therefore if we take the voltage at the output side across the indicated arrow, therefore we are getting 3 times of the peak value of the message signal, or message that means signal generator peak value is possible at the output side. And this is the voltage quadrupler. The quadrupler produces 4 times of the peak value of the signal, and it is obvious because of the presence of the 4 number of diodes and 4 number of capacitors. In the positive sweep, diode D1 is forward biased. In the negative sweep, diode D2 will be forward biased. Again, in the third positive sweep, diode D3 will be forward biased. In the fourth negative sweep, the diode D4 will be forward biased. So in this way we are getting the voltage across the indicated arrow is 4 times of Vm, so it is a voltage quadrupler. Thank you.